Hi everyone, today at the seminar we have Patrick Lin. Patrick, please start.
Hello, hi. I'm Patrick. I'm from the University of Illinois. As it says on my slides, I'll be talking about how to morph graphs on the torus. And this is joint work with my collaborators Aaron Chambers, Jeff Erickson, and Salman Parsa. So to begin, let me tell you what I mean by morphing graphs. The technical mathematical term here is isotopy. But this is a jumble of words here. It's a continuous deformation between two embeddings of the same graph that remains an embedding throughout. I'm just going to show you an example of something that's not a morph and then something that is a morph. So here, in both of these animations, I start with two embeddings of a graph at the beginning and at the end, and I'm animating from the starting embedding to the end embedding somehow. But in the first one on the left, we break this embedding at many points during this animation. On the right, we don't. And so the one on the left is not a morph, the one on the right is. And this is a problem that's been studied quite a bit, both from the mathematical side and from the computer science side. From the mathematical side, mostly we're not interested so much in computing these things, but knowing whether or not they exist. Mathematicians are often interested in whether or not two graphs drawn on some surface are isotopic. From the graphics side, we're actually interested perhaps in computing an animation, and these are nice for visualization purposes and etc. Now, I said from the mathematical side, we're often interested if an isotopy exists, and in addition to being able to prove theorems about when such isotopies exist, we also have a theorem that says, well, in addition to a theorem, an algorithm, in fact, that says, given two embeddings of some graph on some arbitrary surface, we can actually test if this morph exists. Of course, this algorithm is non-constructive, and so in general, we'd like to construct such a morph. And I'm gonna have to nail down a few specific requirements on these morphs in order to actually do anything meaningful with them. And the first constraint I'm going to nail down is that these morphs have to be what I'm going to call straight line, or in the generalization, geodesic morphs. And at least in the planar case, you can think of this as all the edges must be drawn as straight line segments between their endpoints and remain as such throughout the morph. This is really so that we can write down a compact representation of the embedding at all points during this animation in a concise manner. And beyond this, I'm going to insist that these morphs be written down as a series of what I'm going to call linear morphing steps. And a linear morphing step consists of a starting position for every vertex and an ending position for every vertex. And then within this step, it's just going to be linear interpolation. And of course, because the edges already be constrained to be straight line segments or generally geodesics between their endpoints, they're just going to linearly interpolate along. And in fact, the animation that you see on the right here is in fact a morph that's described in terms of two linear morphing steps. In the first step, 2 and 3 move. In the second step, 1 moves. So really, this is so that we can write down combinatorially some kind of morph in some compact way, and that's what we're going to be computing. One of the common things that happens in this sort of planar computational geometry is we don't really need to care about arbitrary embeddings. We can start by working with triangulations and then relaxing to the general case later. And so that's exactly what we're going to do. We're going to spend most of this talk assuming that the graphs in question are drawn in such a way that, well, not so much drawn, but rather all the graphs are such that the faces are triangles as opposed to polygons with higher valency. And then we'll talk about the generalization to arbitrary graphs later on. Well, arbitrary graphs that can be drawn, embedded on whatever surface later on.
So sorry, is this like a technicality, or is it something non-trivial that we can limit ourselves to isotopic triangulation?
It's sort of a thing that just makes certain things easier if we assume triangulations throughout, and then we can relax this later on. A lot of these things we can do without, but it's just it makes certain assumptions. Certain assumptions here just make things easier as we're going along, and then we don't have to think about it too hard. So let me talk about how we might go about constructing such a thing. And I'm going to go back to 1944 with the first sort of useful result in this space, which wasn't even a computer science result, it was a mathematical result. And Cairns here was interested in proving existence of these straight line morphs between two planar graph embeddings. And he actually got really close to an actual algorithm. He stopped just short of it. And the technique that Cairns came up with was this thing I'm going to call direct collapse. And so in this picture over here, if you look at the very beginning, this blue region is where this vertex V can move without causing us to no longer have an embedding of this vertex and its neighborhood. And what Cairns observed is that as long as you have a vertex of degree at most 5, one of its incident edges will be fully contained, well, at least one of its incident edges will be fully contained within this blue region, and so you can move this vertex along said incident edge until it coincides with the neighbor at the other end. Now, you might already be thinking to yourself, we no longer have an embedding if the two vertices are coincident. And that's okay for now, because we'll fix that later. So let's just accept this for now, and we'll be constructing what I'm going to call a pseudomorph that later will turn into a morph somehow. And if we combine Cairns' observation with Euler's formula for the planar graphs, we see that we can always find a vertex that we can perform this operation on. And so that's Cairns' major step here. And so using this, Cairns said, well, suppose you can collapse some vertex V along the same edge in both your starting embedding and your ending embedding. And now you have two embeddings of some graph on n-1 vertices. You recurse. This is quite natural. And then your pseudomorph is just going to be, this thing where you put everything together. And it's quite nice as long as you're okay with a pseudomorph for now, except for the following caveat, which is that the same vertex might not be collapsible along the same edge in both embeddings. For example, here it's collapsible along one edge, but in the first starting embedding, but collapsible along a different edge in the other embedding. This is actually okay as far as Cairns is concerned. Remember, he's just looking to prove existence. And what happened is he said, well, there exists some other embedding. And he didn't even really care to construct it, but we can construct it quite quickly, actually, where V can be collapsed along both. And so we're just going to recurse twice if we're following Cairns' model. And so by performing a sequence of exponentially many of these collapses and uncollapses, we can, in fact, compute a pseudomorph between the starting embedding and the ending embedding.
Where does this collapse twice come from? I think I missed an argument here.
Okay. So I sort of hand waved this argument away. I didn't explain why, but there's some intermediary embedding that we can go through. So we start from the starting embedding. We collapse from V to 3. And then we go to this intermediary thing. We uncollapse from 3. We collapse to 4. And then we recurse again. And then we uncollapse from 4 to get to the final embedding.
Okay. Thanks.
Yeah. So at every stage, we're recursing twice. And then at this point, Cairns gave an argument that said, once we have a pseudomorph, there exists a construction that gets you to an actual morph. The problem with this construction is that it's not really computable. It involves it can involve some fairly complex algebraic curves that in general are not very nice for computational representations. But again, Cairns was just interested in existence, so whatever for him. But then about 70 years later, there was a group of people who became interested in actually taking Cairns' results and then adapting them into something we can actually use. And so they figured out, first of all, how to get around this recursing twice issue and get down to polynomially many, I guess, pseudomorphing steps. And then beyond that, they also figured out how to take these pseudomorphing steps and turn them into an actual morph, so that we no longer have these coincident vertices. And they managed to get a polynomial running time. They didn't analyze it. It's pretty big. So I'm not going to bother analyzing it either. And then in this, I guess in the same year after this paper came out, there were two efforts basically to improve this result. And one of them said, well, we can get down to n squared. And the other result said, we can make them make these steps parallel. And what that means is that in each of these steps, all the vertices are going to move along parallel lines. And this is sort of an odd thing to do because it severely restricts the kind of movements you're allowed. But it turns out this is a good thing because what happens is if you insist on your movements, all of your morphing steps, moving all the vertices along parallel lines, you can prove certain things about these things, and you can construct things that you convert into linear morphing steps, and then somehow this gets you down to linearly many linear morphing steps. And so there was this follow-up paper that got down to there, along with a lower bound that says, in general, you cannot do better than this. At least if you're insisting on writing these things down in terms of linear morphing steps. So this all got culminated in a journal paper that combined all the previous results. They finally actually analyzed their running time as n cubed. And then 2 years later, this running time got improved to something involving the matrix multiplication constant. So that's the state of the art before this paper in terms of planar results. Yes, I forgot this note here that says, these papers called parallel motion something else. But then there's this classical question if you're ever working with computational topology and someone tells you a planar result, which is, what about doing this on other surfaces? And if you're working on the sphere, it's the same thing as the plane. This is a very standard result about planar graphs. But if you look at any heterogeneous surface, the answer before this paper was we have no clue. And in this paper, we sort of answer this for the torus. Right, that was the name of this talk, category morph graphs in the torus. And when I say sort of, so I specifically mean I'm going to be solving this problem on flat tori. And a flat torus has a number of interpretations. The interpretation I'm going to go with is suppose you're playing Pac-Man or asteroids. You're on a flat screen. If you move off the right side of the screen, you come in on the left. If you move off the bottom edge of the screen, you come in on the top. And on the right here, you can see an example of a graph that's been embedded on the torus and being animated between two embeddings. You'll notice for example, that between 0 and 1, there are no fewer than 4 distinct edges here that wrap around the torus in different ways. It's sort of a minor technical point, but these are distinct edges. We can have parallel edges and self-loops on toroidally embedded graphs because they can wrap around. And these are distinct geodesics, so it's okay. This is a sort of a minor point, but it does end up being an important thing to consider at certain points in this algorithm when we're trying to construct these things.
But what do you mean by sort of? Like, isn't it like the definition of a torus?
What do you mean?
Like like you just divide R squared by Z squared and squared, and that's
the definition of a flat torus. That's the definition of a flat torus in terms of geometry.
Oh.
Okay, so topologically, all tori. So topologically, you can always define a torus as R squared mod Z squared, and then you can think of this either geometrically as this square with where you in this Pac-Man or asteroids type square, but people generally think of tori as being the surface of a donut, like in this picture over here, and geometrically that's very different from being flat. Right, geometrically, there's curvature in the donut picture, and in the case that I'm looking at, I really think of it as I'm locally Euclidean always, geometrically, not just topologically. And there are many reasons that I restricted myself to this case, and most of them is because the curved case is difficult. And I don't
yeah, that makes sense. Yeah.
There are a number of reasons why people care about flat torus graphs. One of them is this classical topological reason of what about heterogeneous? But also, flat torus graphs also happen to capture this nice family of infinite biperiodic planar graphs that a lot of people work with. And hey, look, as a consequence of dealing with flat torus graphs, we now have a new visualization technique for these graphs that people care about. So if we want to, construct these morphs, this kind of morph on toroidal graphs, given that I spent so much time talking about Karen-style direct collapses, the first question is, well, can we do this on the torus? Because if so, we're probably done, right? Modulo all of the work that went on in the 2010s. Except we are immediately stymied by the fact that Euler's formula for the torus implies that we might have average degree exactly 6, and hey, look, here's an example of a vertex with degree exactly 6 and its neighborhood, and this blue region that this vertex can move around in, and we find that we cannot do a direct collapse here. Okay, so it looks like we're stuck, especially if we're in the situation where every vertex is degree 6, right? It turns out everything is fine. And this turned out to be a fairly non-trivial exercise. And the proof ended up being quite subtle. It was very fragile, and it's this proof by contradiction that starts by like looking at all of the pieces of this and looking at degree counting, angle counting, and a bunch of other things in order to establish, okay, somehow in this bad situation, all of the vertices have to have neighborhoods that look like one of these cats or dogs at the bottom here that I've just accidentally covered up with this Google slide stuff. So somehow we end up with a situation where all the vertices have to look like one of the bottom 2 pictures, well, at least their neighborhoods have to look like this. And then we'll start looking at these. Things that we found after looking at a bunch of counting arguments, and we start looking at, okay, now that we know every vertex has to look like this locally, what about the neighbors? Or do the neighbors, if the neighbors also have to look like one of these 2 things, what has to happen? And one of the things that happens is that if you look at one of these things that looks like a dog, sort of from the side, and you look at its nose, it can't also be a dog. Okay, so now we've characterized something by looking at this geometry of these cat and dog looking things, and after applying these geometric arguments, we have some more things that we can look at, and then finally we say, okay, so we have to have a cat somewhere in there, and then we do a bit more geometric arguments, and then we move away from the geometry to looking at the topology of these embeddings and saying, okay, so what happens if we start analyzing the topological properties, and then topological arguments go here. At the end of the day, we end up with this contradiction that basically says, this situation that we have cornered ourselves into, it's just impossible. These cats and dogs do not get along. Okay, so after a bunch of fairly fragile arguments, we end up with finally with this contradiction that says, okay, we can do this. We can always find, at least in this special situation where we have no self-loops, we can always find a vertex that can be collapsed. And here's a nice animation of just doing this on the torus. And then if you think back to what I was saying about Karen's, about some vertex not being able to be collapsed along the same edge, actually, if we find a vertex that can be collapsed in one embedding, it might not be the vertex that's collapsed in the other embedding. Oh no, except we can go back to this Karen-style argument about there being some intermediary triangulation that we can go through, and then we recurse twice. And at this point, we've basically generalized Cairns to the flat torus. We have somehow reproduced this result that there exists a morph. There's always exists a morph, except for the part where we kind of needed to start up by assuming that there exists a morph. So really the thing that we've proven here is if there exists a morph between these 2 embeddings, in fact, there exists a geodesic morph. That's really what we've reproduced here in terms of Cairns. But remember, I cited all of these results that improved Cairns' result on the plane to optimal number of morphing steps computed in this fairly low polynomial running time. Except for there's this sort of problem that most of these results don't generalize to the flat torus. So we're basically forced to ignore them and come up with something new. And the something new that we came up with involves these spring embeddings. So I think these are familiar to many people. It's a bunch of words here, but effectively, you start with some planar graph embedding, and you assign a weight to every edge, and you solve a certain linear system, and it gives you this much prettier embedding where every face is convex, every vertex is a convex combination of its neighbors. And it turns out that you can always do this on a torus as well. So you start out with some embedding, you do exactly the same thing, you get a prettier embedding. Now, Colin-de-Verdier actually proved this in quite general terms. You can do this on any surface of heterogeneous as long as it has a negative curvature everywhere, except that the solution on the plane and on the flat torus, you can do this. You can find this embedding by solving a nice linear system. In general, you can't, and that's going to be a limitation in heterogeneous. But because this paper was in French and it was kind of buried in math journal, nobody knew about it for many years, and so it got rediscovered a few times in the 2000s. Oh well, so it goes. But we will be making use of this generalization. And specifically, the way we do it is the following. We're going to really take advantage that on the torus, we can compute this by solving a certain linear system in n to the omega over 2 time using toroidal separators and nested dissection, etc. And it's this thing that we're going to call a spring collapse. And specifically, this is what we're going to do. Suppose we start off with a spring embedding. Okay, we're going to really restrict ourselves to spring embeddings for now. And this is going to be okay. And what happens is if we take the spring embedding and we look at its weights, or the weights on all the edges, and we take one of the edges and we increase the weight on that edge to infinity, what's going to happen is that it's going to look something like this. As it goes to infinity, it pulls the two endpoints closer and closer together until they coincide. And so now we have a pseudomorph that collapses this edge. And the result is another spring embedding. It's going to be a spring embedding on n-1 vertices. Now, what the special thing that happens here is that this pseudomorphing step is parallel, but not necessarily linear. But that's okay, because the special thing about parallel pseudomorphing steps that the planar people made use of is that we don't care, actually. If everything's working in parallel, we can just take the starting position, we can take the ending position, and we will just linearly interpolate, and now you have a linear morphing step, or sorry, linear pseudomorphing step. And so all you really need to do is figure out from the starting position what the ending position is going to be, what it's going to look like if we just set this weight to infinity. And this can be done by solving one linear system for the positions at the very end. And so that's very nice. Now I want to talk real quick about this one special case. But with the Selfloops, because I mentioned earlier that we can't do direct collapses. We don't necessarily have the ability to do direct collapses even if all the vertices have degree 6, if there's a self loop. But actually, that's the easiest case, it turns out, surprisingly. Because what happens is if you're in the situation where you have a self loop and every vertex is degree 6, it turns out you have a bunch of self loops. Every vertex has a self loop, and all these self loops are parallel to each other. And so you have this nice little sliding thing that you can just solve. This is going to be a very nice base case to recursion. And so at this point, we have this nice situation where at least if you're going to be collapsing, doing direct collapses, we can always do it. And there's a nice base case at the end when you can't. I suppose I shouldn't have said always can do it. You can do it most of the time, and when you can't do it, there's a nice base case. So how are we going to put this together with the spring collapse thing? Well, sorry. One of the things that happens in a lot of computational topology algorithms is that you compute some kind of animation or some kind of homotopy or whatever to some canonical representation of the thing, and then you move away from the canonical representation to whatever you have at the end. And that's exactly what we're going to do by considering this spring embedding to be our canonical representation. And so we're going to start by saying, let's take an arbitrary embedding and an arbitrary spring embedding of the same graph. By default, we can just set all of the weights to 1. And if we compute a pseudomorph from this arbitrary, if we compute a pseudomorph from this arbitrary embedding to the spring embedding, we can reverse this to get a pseudomorph from the spring embedding to the target, to the initial embedding. And so if we want to compute a morph between two arbitrary embeddings, we can do this twice. Right? And just use the spring embedding as intermediary. So all we really need to do now is compute the pseudomorph between the arbitrary embedding and the spring embedding. And so on the one side, we'll do a direct collapse when we can, because we know we can, as long as there are no self loops. And on the other side, we can perform a spring collapse. And if we perform a spring collapse on the spring embedding, well, the result is another spring embedding. And so instead of recursing twice, we just need to recurse once, because we have, we're back in the same situation as we started in, except on n-1 vertices. And so we at the bottom, we do this thing that I showed you where we just slide things around if we are in the situation where we have self loops. And as I said before, we can just combine two of these if we need to find a pseudomorph between two arbitrary embeddings. If you analyze the running time for this recurrence, we find that quite amazingly, the number of steps is linear, which matches the best known result that I cited for the plane. And actually the running time is also the same as the best known result for the plane. This was sort of magical that it turned out this way. I've sort of brushed off computing actual morphs throughout this entire thing and told you how to compute pseudomorphs. And that's because it turns out that once you're in the situation where you're computing a pseudomorph where every step is a parallel linear pseudomorphing step, which is the case in terms of these direct collapses and these spring collapses, there's this result in the planar case, and this is really what allowed them to get really far, that just says, well, yeah, it's really easy to convert this kind of pseudomorph into an actual morph. And it turns out that if you just stare really hard at it, it turns out that however many pseudomorphing steps you have at each step of the recursion, you just add one in order to get a proper morphing, to get a proper morph at the end. And so we redo the analysis, and the asymptotics don't change at all. And so at this point, I have given you at least morphs between triangulations. If you want to morph between arbitrary graphs, it turns out that the spring embedding idea is really nice because it bypasses a lot of pain that happened in the plane about trying to go from non-triangulations to triangulations. They had to come up with a bunch of different triangulation techniques that were compatible between the starting embedding and the ending embedding. And now we bypass a lot of that pain by basically observing that if we start with the starting embedding, and we can triangulate it arbitrarily, okay? And in the spring embedding, all the faces are convex. So we can triangulate the the spring embedding in the exact same way to get a compatible triangulation on the spring embedding. And so now we'll just compute this morph between these two triangulations, and we'll drop the additional edges. And what happens is, for the other half of it, if we are trying to get from some embedding to another embedding, for the first half, we can choose a triangulation that's compatible with the starting embedding. With the second half, we choose a different triangulation that's compatible with the ending embedding. And now we don't care about compatibility between the start and the end at all, because the spring embedding in between is compatible with both. And if we're just dropping the additional edges, we don't really care. And so this bypasses a lot of the pain that happened in the planar case about trying to come up with compatible triangulations. And so, once again, it's this thing where we go to the spring embedding and then we go out from the spring embedding. Really, this doesn't change the asymptotics at all, because we're just doubling things. So at this point, the conclusion is that, well, we've improved cairns, or we extended cairns to the torus. So we have these geodesic morphs. And somehow this was new. Despite the fact that we have these algorithms that tell us if we have more morphs, we don't actually know in general if we can actually find geodesic morphs between embeddings. And so we here, as a side consequence of actually constructing these things, we know that they exist. We can also compute a morph between, there's sort of a technicality here due to using spring embeddings, essentially 3 connected geodesic torus graphs. And these things match the best known running time in the plane. What I really like about these results is that it actually, in my opinion, gives you a simpler result on the plane. So especially this idea of going through the spring embeddings, it's very powerful, it's very nice. And in fact, it works on the plane as well. So this really simplifies things on the plane. At the time of writing this paper, there were a few open questions, and I've actually answered one of them at this point. And I want to spend a little bit of time just glossing over that result. But let me get to some of the obvious things first. The first one is that if you think hard about the fact that I requires the spring embedding thing, at least on the plane, the usual thing is this requires 3 connectivity of the graph in order to compute a proper spring embedding. And this is a thing where, at least on the torus, we believe that we can get around this sort of by, we can get down to essential 2 connectivity and lower the connectivity requirements. It's not too difficult, we think. The other issue is that I set up a bunch of ground rules about writing down these geodesic morphs that are written down in terms of these linear morphing steps, particularly because I wanted a nice combinatorial representation of this morph that I can write down fairly compactly. The problem is that the perturbation method that I'm citing and solving these linear systems can require fairly high numerical precision. And at least the sort of a general thing that computational geometry does is if we work in the real RAM or a certain real RAM, then we should have just ignore this. But practically speaking, it's kind of runs counter to this philosophy that I set up about writing down compact representations. So it'd be really nice to get some version of this that doesn't require this high numerical precision and get around that. But this is also something that affects planar results. Then there's, of course, this classical question of what about heterogeneous? And so, as I mentioned before, Coulomb-de-Verdier's spring embedding theorem actually extends to heterogeneous surfaces. But computing these spring embeddings via this linear system and their notion of this being a parallel morph both require flatness. I don't know what it means to do this on heterogeneous surfaces at all in a way that's computationally meaningful. Of course, we can solve for the spring embedding by doing some kind of convex optimization. And so if you're in the world of graphics or scientific computing, you don't care. But if we're working with combinatorial algorithms, this is not so nice. And the other issue with going to heterogeneous surfaces is that the analysis of extending cairns to the torus via this direct collapse, it's very fragile. It really requires a bunch of stuff that's specific to the torus. Once you go to heterogeneous, then we have no clue what's going on in terms of direct collapses anymore, and it's quite annoying. Now, on the plane, there are a number of other approaches that I didn't talk about. One of them is this result by Floder, Grossman, Shirashki that adapts a different generalization of touch spring embedding from Coulomb-de-Verdier's. And there was this open question for many years about whether or not we can do this on the torus. And there were a bunch of attempts that basically failed. And Jeff and I think we've solved it. And along with this actually is yet another, as a corollary of this that was pointed out to us by Anna Lubov, is another algorithm for constructing morphs of planar graphs and torus graphs that have linearly many linear morphing steps computed in the exact same amount of time. So actually, this paper that we haven't written yet is going to actually even simplify this presentation even more. Here's the problem. It's because it involves solving linear systems, it still suffers from the numerical precision issue. It still suffers from the issue of we don't know how to do this in heterogeneous surfaces. There's this other result about morphing where why are we insisting on straight line segments between vertices? Why not allow them to bend somehow, right? We're not going to increase the complexity by too much if we do this, right? As long as we control how many bends we can incur in edges. We haven't looked at this. There's this other result about morphing between orthogonal embeddings. This is really nice if you're thinking about things like VLSI or circuits, where you want to print, you want to print graphs in such a way that all of the edges are drawn as either purely vertical or purely horizontal. And then people thought about, well, what about morphing between these embeddings? There's a slight problem that immediately occurs if you're trying to do this on the torus, which is that even drawing graphs orthogonally on the torus is not a solved problem yet. So we're not going to even touch that. One of the ways that people on the plane tried to get around this numerical precision issue is that they try to morph between Schneider-Woods embeddings. Schneider-Woods embeddings are these really nice embeddings that allow you to get really low precision descriptions of embeddings. And what happens is if your starting embedding is a Schneider-Woods embedding and your ending embedding is a Schneider-Woods embedding, you can compute a morph that goes basically strictly between Schneider-Woods embeddings, and then you get extremely low complexity description of the morph overall. The problem is that, well, there are two problems. The first problem is that not all graphs are Schneider-Woods embeddings, and it's unclear how to morph from an arbitrary embedding to a Schneider-Woods embedding in low complexity. The second issue is that Schneider-Woods embeddings on tori are well, they're not super well understood. There was this big paper about Toroidal-Schneider-Woods embeddings, but the implications of these things are not nearly as well understood as Schneider-Woods embeddings on the plane. And in particular, we still have this issue, right? Of if we're trying to morph between arbitrary embeddings, they're very much not Schneider-Woods embeddings still. So we still have this other issue. This is a nice first step, right? About taking these ideas from the plane and saying, can we do this in heterogeneous? But it's very far, at least in my opinion, from where we would like to get to. In particular, it suffers from a lot of issues that I really don't know how to get around. So that's the end of that talk. I was working under the impression we'd have time for some questions, but I don't know.
Yeah,
Sure.
We do.
I mean, I have several questions.
Yeah, so maybe go ahead, Przemek. I have some too.
One question is, it's not clear to me, why is this the time is omega over 2 for solving those linear systems? I was under the impression that solving the linear system is n to the omega.
Right. So
it means it's a smaller system, right?
Oh, sorry. Yeah, no, it's here.
Yes.
Okay. So there's this sort of well-known result in the plane where if you're solving a linear system whose support is the vertices of the plane, then you can use planar separators along with this technique called generalized nested dissection to solve the linear system in O of n to the omega over 2 time.
Okay, I was under the impression it will be planar separators.
Right. So it turns out that if you're working on the flat torus, there are these things called toroidal separators. They work exactly the same way as planar separators. So you just black box it. Yeah. So that's where we get omega over 2 time.
I wish Pavel was here. He is a connoisseur of planar graphs. Okay, I have one more, I think, more open-ended question. So when you were talking about this very delicate proof in those cats and dogs.
Yeah, this one.
Yeah. Every time I'm encountering such a situation, there are always several questions that come to mind. Like usually we don't believe that the universe works in this way, that such a complicated proofs are necessary.
Right.
And of course, there is like a huge potential for omitting some case.
Right.
Are there in general any approaches to either formalize it or automatize it?
These difficult cases?
In general, I mean, let's forget even about the particular problem we are working here with and go into the general field of graphs embedded into surfaces. Right. And I have a I want to certify that certify that my proof is correct. Mm-hmm. I want to certify that I have covered every case. Are there any attacks, approaches to certify, to formalize? By automatize, I would also mean trying to employ some automatic solvers.
I have not thought about this. I have not really looked into automatic proofs of this kind of thing.
I know it's totally random and
and also
not a question.
There's also this other thing where just sort of because this proof is quite delicate. I mean, in some sense, it's very nice to know that this result is true, but also at least the feeling it gives me is that this is not the right approach. This is the approach that worked for us for now, right? But it is not sort of the thing that we really want to go with, especially if we want to be able to generalize this further. It's just partially because it is so delicate.
So do you believe that it can be sort of simplified, or that you can build a much more general framework for this?
Well, so I was talking about here with this barycentric interpolation method that I claim that will appear soon. Hopefully, it actually will. One of the ideas in here is that we can get linearly many linear morphing steps in the same amount of running time in this way that bypasses this Karen-style direct collapse completely. There are many reasons to believe that, at least for visualization purposes, Karen-style direct collapses are just not the right thing anyway. They're awful for visualization. You move everything almost to the same point, and then you expand back out. It looks terrible. So in addition to being mathematically fragile on the torus, it's also not the one that we want to use anyway. So yeah, hopefully, we work out all the details of this and everything turns out right and we get this simplified version and I don't have to talk about direct collapses again.
In the previous approaches for planar graphs, the complexity was the same. It was 1 plus omega over 2.
Yeah.
Where does that omega over 2 come from?
Okay. So hold on. And let me find the slide. So this one over here. So this one plus omega, this omega over 2 actually comes from, they were able to figure out how to adapt the Floater-Gossman-Shirashki approach into basically a subroutine that replaced a black box in the previous result. And so the black box that was previously used had n² running time, and they replaced it with a subroutine that takes n to the omega over 2 time by solving one instance of the Floater-Gossman-Shirashki linear system, which is a different generalization of the spring embedding. Yeah, that's where that running time came from.
Is there any intuition? Is it?
Do we expect some planar separators there?
No, is it a coincidence, or is this like, okay, that's probably
not
the right answer?
I think it's maybe not so much. It's not really a coincidence. Insofar as if you believe that spring embeddings are a useful thing to put in your toolkit for working with planar graphs, then it is not a coincidence. Because they're, instead of working with Tut spring embedding, they're working with a generalization of Tut spring embedding. And so they are using that in order to move basically between two I guess barycentric interpretations of their embeddings, and by basically interpreting these things as generalizations of spring embeddings, this is sort of a natural thing that comes out. Yeah. And in fact, this technique is, it was pointed out to me that I think there were a number of other people who have used this approach when working with graph embeddings. I think there's this older paper of Krobach, Goodrich, and Tomasia from, I think, sometime in the mid-90s about drawing graphs in various dimensions that also use a similar approach. So it's a useful, I think it's a useful idea when working with planar graphs. Can we use a spring embedding somehow?
Okay, now I would like to ask you a few things about like geometry of this. So yeah, we talked, like I asked about this flat torus, right? Before, yeah, and you're right that actually like this geometrical torus actually it has more structure, right? Yeah. So do I understand correctly that if you take a geometrical torus, then you have different geodesics there, right?
That's right. That's right. So in particular,
and is it the obstacle actually? Like is it the obstacle or is it something else?
That is the obstacle here, because geodesics, when you have positive curvature, geodesics are weird.
Okay.
When you have uniform non-positive curvature, so flat here plus negative, if you have there's only one geodesic that wraps around in a given way. So for every way that you can wrap around the torus, there's only one geodesic that does that. Now, first,
what do you mean?
Okay, so if you look at the graph on the right here, between 0 and 1, I can go from 0 to 1 by going from just going without crossing any of the boundaries. Okay. There's only one
Yeah.
geodesic that can do that. If I want to cross strictly the left boundary, there's only one geodesic that can do that between any between 0 and 1. In any if you just fix the position to 0 and 1, there's only one that can do that. If I want to wrap up and over, there's only one geodesic that can do that.
Yep.
Okay, but if you start introducing positive curvature, you can have multiple geodesics.
Yeah. I can imagine.
And especially
that.
depending on how complicated your geometry is, you can have infinitely many, in theory, that wrap around in the same way. This is most easily done by taking a bunch of bumps. You're just taking this flat torus and you're just giving it a bunch of hills, and then every time if you wrap around the hills in different ways, now you have number of geodesics is immediately exponential in the number of hills that you've created. Right, any combination of wrapping up above them or below them, and that's just painful to work with. I don't know how to deal with that properly.
Yeah, like I was going to ask also if there are attempts to actually like show results like this for, I don't know, like Riemannian manifolds or something like this, where you can have like different geodesics and stuff.
So in some sense, the thing to do there is to no longer insist on geodesics. You can insist on sort of this piecewise geodesic situation instead. And sort of the standard representation, if you're not looking at the flat torus, but some Riemannian surface and say embedded in R3, is that you write down some simplicial complex or some triangulation of the surface in R3, and this is your canonical representation, and then your graph is described with respect to this triangulation. So you say every vertex, your vertex positions are given by here is its coordinate within a certain triangle in this triangulation of the surface, and the edges cross over the following sets of edges in the reference triangulation in a certain way. And that's actually the context in which this algorithm that I cited about existence of a morph, they actually say, well, if you are given a graph embedded on any arbitrary surface that has been described by some reference triangulation, we can do it in O of n time. And if you stare at this flat torus, you say, there's a very obvious triangulation here. You just draw a big diagonal, and then really nothing has changed.
Yeah.
Right. So we can apply it's sort of a very big hammer that we just say, yeah. In this simplified setting, of course, it still works. But I think there's sort of a reason why their algorithm is non-constructive. It's because it's kind of hard to deal with doing the actual geometry in these sort of spaces. The topology turns out to be much easier if you don't actually have to care about actually moving things around. If you're just caring about checking certain properties.
Yeah, and by the way, how heavy are tools, like mathematical tools that are used in this area? In a sense that, like when I look at this result, it looks like you employed like some kind of results, like at least terminology from algebraic topology and stuff. When we like talk about this simplicial complexes, the first thing that comes to my mind is homological algebra, and I would just like know if you will like use it heavily, or is it like, yeah, we have this terminology and stuff, but we mainly like use some combinatorial arguments and
very often we just use combinatorial arguments. One of the things that ends up happening here, so after a bunch of combinatorial arguments and geometric arguments, we actually do end up using sort of a big hammer from topology. It's not something that just applies to combinatorial surfaces. It applies to surfaces, surfaces in general. We do cite some heavy results sometimes. I think by and large, at least. The people that I know and talked with and work with, we try not to, whenever we can, to apply extremely big hammers. In particular, the theorem that was applied here in the Zemesnik-Cohen-Verdier paper, it's very nice in that you can actually sort of understand without too much prerequisite material. You can actually understand what the statement of the theorem is that allows them to get this algorithm. It's almost entirely combinatorial in its approach, and that's really how they get their algorithm so quickly. And so in general, I think this is especially the thing that Jeff Erickson likes to do, is he likes to look through the old literature back before the invention of a lot of this heavy technical machinery, and say, well, can we leverage some of these results and come up with simple combinatorial algorithms that can be reasonably described without too much baggage?
Great approach.
Yeah.
Yeah, and another thing is, like you mentioned, like this open problem. If we can do these algorithms without this perturbation method, yeah. But do you actually want to get the same time complexity, or are you content with something slightly slower?
So one of the things about so I'll answer that in two parts. One is this barycentric interpolation method. We can actually use it to, in fact, simplify the planar results already. So we don't have to deal with this perturbation method at all. But the problem is that it still involves solving linear systems. So we still have this high numerical precision issue. But it looks better. It looks significantly better. All right. If at least if you're thinking about this from a visualization point of view. The other thing about time complexity, I'm happy with, I think I'd personally be happy with anything at all right now in terms of homogeneous surfaces, or even on the plane or on the torus, if we can get around this high numerical precision issue, right? Yeah, I'd be pretty happy if you can get around that at all.
Yeah, because my point is that you have omega in your complexity already, right? And it's hard to imagine to get something else, which is like as fast as this, and without like trying to solve some linear system or anything.
You'd have to bypass solving a linear system, right? You'd have to be able to do this without that.
Yeah.
I think that my conjecture is that you're definitely not going to beat n squared, just due to the nature of the constraints that we've set up, right? Every linear morphing step has to be described by O of n positions, right? And in general, you're going to need O of n steps. So n squared is basically, I think there's no reason to believe that you can do it faster than n squared anyway.
Yeah, so if you believe that omega equals 2, then your algorithm would be optimal, but on the other hand, like it's not very practical.
Right.
Yeah, nowadays. Sure. And by the way, is there any possibility that people would use algorithms like this in practice, like from morphing stuff?
So this one in specific, maybe not.
Okay. Yeah, like on torus, probably not.
But no, not the torus issue. It's the Clarence's direct collapse thing that's the issue, right? It's not very good visualization. But there are good reasons to want to morph things on torus graphs. In fact, when I was doing the background literature survey for this, I found a result in Chi, specifically about whether or not it's actually a good thing to try to use heterogeneous surfaces to visualize networks. And they found that, yeah, hey, let's do this. So that was a Chi paper. People care about drawing graphs on tori. It's not some niche thing that nobody cares about. It's actually useful for visualization purposes. And if we can move things around, right, in a way that's visually nice, that's a good thing, right? And so among other things, I'd have to implement this and test it out later on. But the barycentric interpolation method that I keep claiming will appear, that one I believe will actually be fairly nice to look at. I think that one will be somewhat useful. People in graphics, if especially in situations where they don't care about complexity issue, description complexity issues, and they don't care about possibly breaking the embedding at some point in the middle, they actually use Floater-Gaussman. It produces very visually appealing animations most of the time.
Yeah, that was what I thought, that like in practice people like they don't care if you actually like cross like these things, right? But
Yeah.
if it's like visually pleasing anyway, right?
Yeah, and it's more like as long as we can get away with minimal crossings,
Yeah,
then
yeah,
we're
yeah.
happy, right?
Yeah.
But it's just, in general we haven't. It's very hard to control the number of crossings that have, the maximum number of crossings that occur. Unless it's 0, right? If it's 0, then we can come up with all these schemes. Yeah.
Yeah, by the way, is it like a good question to ask if you can like morph with one crossing or whatever?
Yeah, I think these are good questions to ask. Can you can you come with something faster, as long as you don't have many crossings? So one of the, I think maybe I don't know if I can draw this very well, but maybe I'll just sort of vaguely hint at it. But the lower bound example for why you need linearly many morphing steps is basically if you have this spiral that looks like this. It's not staying, but basically you have to untangle it vertex by vertex.
Okay.
If you want to morph that into a straight line segment, you have to basically untangle it piece by piece, and it takes forever to do. But if you start a lot of crossings, right, and you can control the number of crossings, you can actually get to fewer steps, right? Now, can you get down to, actually asymptotically smaller than linear? I don't know. I haven't really thought about it.
Sure. Yeah, makes sense. Yeah, I think that's all I had in mind.
I have no more questions. Let me just stop the recording.
Okay.
Thanks for the talk. It was really nice.
Mm-hmm.